Okay, this is part 2 to the last video I was filming. The last video I was talking about how do we generate the sinusoidal voltage and our third harmonic injection voltage we need to generate a desired current in a load, and determining that based off of the modulation index and the power factor. So we left off with showing that changing the power factor shifts the phase and the voltage apart, and by turning off different switches we can put voltages in different sectors like this in order to create a sinusoidal fundamental voltage that we use to drive our load. So then after this, what my script is doing is it's taking the information we know of when are the high side switches, when are these high side switches on and off, and what is the current through the load at that instant, in order to determine what is the current coming from the DC link. There's a paper. This paper is basically an estimation technique for determining the DC link voltage ripple, and we'll get waveforms like this soon, but they have some like envelope stuff. I don't really, I'm just calculating the waveform as is. They're trying to calculate what is this envelope as some analytical method, but anyways, the point is when the high side switch is on, the current in that phase is the current coming from the DC bus. So then the current coming from the DC bus is the combination of the current in all the high side switches, basically. So how do we take our arrays and turn it into the DC link current? Let's see. Here, now determining current coming from DC bus. Current in from DC bus equals current through top side switches. So current from the DC bus is going to be equal to current in phase A times the state of switch 1. So this S1 variable is always going between, you can see it's either 0 or 1, and when it's 1 that means the high side switch is on. So, oh, scrolled way too far. God, I'm lost in the script. Okay, so phase A, which corresponds to switch 1, whenever switch 1 is on, then the current coming from the DC bus is partially that phase A current. So then we add the phase B current times the state of switch 2 plus phase C current plus the state of switch 3. And then this is just doing the same, but for the switch states in third harmonic injection / space vector PWM, which should have the same switching states. And this makes it so that we can get this array called IDC bus and IDC bus for third harmonic injection, and this is the current coming from the DC bus. So let me change the power factor back to 1, and then we'll look at the plot for the current. This takes a while. It just takes a while because the way I have the script set up right now, it's running through this for loop 6 times because like in the last video, I was trying to show how if I filtered out the pole voltage high frequency components, you can see the fundamental voltage generated by the PWM is actually sinusoidal at the fundamental frequency slash sinusoidal at the fundamental frequency plus the third harmonic if we're doing third harmonic injection or space vector PWM. But running it through this for loop just takes a lot of time. So this takes a while to load. But let's see, once it loads, we'll be able to see the DC bus current for a purely resistive load or almost purely resistive load. Okay, there we go. So, whoops. So here, I also have this single variable that's just the average of this plot of the current in the DC bus. And looking at the DC bus current, you can see that the fundamental frequency, the fundamental repetition of this DC bus current is actually at a frequency that is 6 times the fundamental frequency. So this whole length of this plot is one fundamental cycle, but because the current coming into the DC bus is the combination of those 3 currents, you can see this is actually the envelope of the 3-phase currents when they're coming in. So basically it's like, you can see in the different vector states, you can see, let's say in this state, current is coming in this phase and going out these 2 phases. So then in this state, the current into the DC bus is just the current of phase A. So, and then in the case where phase A is negative, it's the current coming in these 2 phases and then coming out phase A, and those sum up to phase A, so it's basically the current coming out of phase A. So if you just look at this envelope, it's like if you flip this peak up here, you would be able to trace out 6 of these peaks in one fundamental cycle. Let's go back to that. So the fundamental repeating frequency is 6 times the fundamental. And then you can see there's also the component of the switching frequency within this. And I have the bound set to the negative peak phase to positive peak phase because I will change the power factor, and we'll see how this current isn't always a positive sign. But so let's zoom into this for a moment. And so this current is basically the sum of those top 3 high side switches, and that's the current going in to the 3-phase inverter. And obviously this is the reason we have a DC link cap, because without it we would have an insane ripple, and it would just basically have this really, it just wouldn't be good for our DC bus. So let's change, or actually first let's look at the third harmonic injection. So this is with sine PWM, this is with third harmonic injection. It basically looks the same, but there's actually like some slight differences you can't really tell right now. But the average DC current in is the same because we obviously have the same, we're driving the same 3-phase load, so we're going to have the same DC input because the power in is going to be the same as the power out in an ideal world with no losses, right? So now I'm going to change the power factor to, let's see what it looks like at, let's just try at 0.5. Okay, now it finally loaded with a power factor of 0.5, and now you can see that the current actually from the DC bus goes negative. And that's because the power factor, since the voltage and the current are since the current is lagging the voltage now, when you multiply the instantaneous power of this equation, the power actually goes negative as well. So if the power out has decreased, then the power in also has to decrease. And the power in decreases by supplying a negative current. And this would be really bad for the battery, because if you imagine the current being going in and out of the battery, having this AC component in the battery will heat up your battery, and eventually, if it's bad enough, it'll probably blow up your battery pretty much. So here you can see with a power factor of 0.5, the current actually goes negative, and that happens when, you can see that happens when the current is actually, well, that's basically happening because the sum of the high side switch currents is a negative value, right? And that's happening because you have this lagging of the current. There's going to be times when you're opening the switches to apply this voltage, but the current is, the total current is still negative. So let me change the power factor to 0.0. So now with the power factor of 0, let's see what happens to the DC link current. Look at that. Look at that. So as you know, if the power factor is 0, you're basically delivering no power to your load anymore. So then the phase current and the phase voltage are going to be 90 degrees out of phase. Here you see they're 90 degrees out of phase. So when you multiply them together, get the instantaneous current, or the instantaneous power, sorry, you'll see that the average power ends up being 0. And when we look at the DC current in, we get 0 current in because we have 700 volts on the DC link, but the power factor on the output is 0, so the power in needs to equal 0, so 0 times 700 equals 0. So now you can see that the current is always going in and out, and in and out, and in and out, and in and out, and in and out, but it's always an average of 0. So the power is constantly like swishing and swashing back and forth between these. And obviously in an ideal world there's no losses due to this, but if you have any sort of losses in this system, you're gonna just be wasting power for no reason. So let's switch it back to, I don't know, we can keep it at 0 for now and see what results we get. So this is the instantaneous current from the DC bus. And the instantaneous current from the DC bus is going to have a DC component that is the actual power you're inputting, and it's going to have an AC component that's going to be due to the switching frequency and the power factor of the load. So the total current in on the DC bus is going to be equal to the DC component plus the AC component. So the point of the DC link capacitor is to handle all of that AC component of the current, is, like I said, you don't want an AC current coming from your DC battery because that's going to cause a lot of extra heating and be very dangerous for your battery. So I'm calculating what is the current going through that capacitor, and the current through the capacitor is basically just going to be the total current in minus the DC component, because like I said, the total current in is equal to the DC component plus the AC component. So the AC component is equal to the total current minus the DC component. And the way I'm doing that in this script is I'm not actually subtracting out just the DC component. I'm doing an average window of the average current in, just in case there's any variation over time of some really low frequency component, so that we don't get any errors as we integrate later. We'll see. So basically, let's look at this zero power factor load first. Here in orange is actually plotted the current in, and because we have a zero power factor load, the current in is 0. And then in blue is the current through the capacitor. So because there's 0 DC current in, the total current in the DC link is actually just all the current being handled by the DC link cap. So then I have this other calculation. I'm calculating the RMS current that's going through this capacitor. So I'm taking the array of this plot of the current through the capacitor, and then I'm taking the RMS value of that and then just multiplying I squared times the equivalent series resistance of that DC link. And at the beginning I said the DC link ESR was 1 milliohm, and we have 4 capacitors. So 1/4 of a milliohm is the total ESR, which is super low. So then you end up getting, you can see for sine PWM, we have 33 amps RMS through these capacitors, but the ESR is super low, so you end up burning like 0.3 watts. And then for third harmonic injection PWM, we have a similar amount, and also like 0.3 watts of loss. So then after this script is calculating what is the DC link voltage ripple caused by this current. So this is all the plotting. So here, calculating DC link voltage ripple from capacitor current. So fundamentals, I equals CD VDT. So then if we just do some algebra, the change in voltage is going to be equal to the change in time multiplied by the current divided by the capacitance. So because we have an array that has these discrete steps in time and discrete steps in current, I'm using this for loop. And what this for loop is doing is it's saying the change in time between two steps, dt, is going to be equal to the time at step n plus 1 minus the time at the current step n. And then for sine PWM, we're taking the capacitor current for sine PWM. So the capacitor current at step n plus the capacitor current at step n plus 1 divided by 2, I'm saying is the average current between these two discrete steps. And so then we get I, and then we have C from the beginning. That's one of our input parameters. So then we say dt times the current at this discrete time step divided by C is going to be equal to the change dt or dV in voltage over this discrete time step. So then I have to initialize the ripple current. I'm initializing the ripple current as 0. So then as this for loop iterates, it's basically adding these little dV steps within each of these discrete time steps. And then from this we can plot it, and here we see what the DC link voltage is. So right now we're getting pretty crazy 43.8 volts peak to peak on this sine PWM, and 43.5 volts peak to peak on this third harmonic injection PWM. And basically, this plot is just the voltage ripple on the DC bus. So I didn't plot it with the DC bus, but you can see this is basically at the same frequency as the switching frequency, with that really low frequency 6 times the fundamental envelope. And let's go ahead and change the power factor again. So let's see with a power factor of 1, what do we get? Alright, now we can see with a power factor of 1 how the voltage ripple has changed. And like I said, remember with a power factor of 1, the DC bus current is always positive value. So then the average AC component, so we're going to, for the AC component going through the capacitor, we're going to take the total current here and subtract out the average. So then we get this, and then in the orange we can see the average current in the DC link. But the current through the capacitor is no longer, or it's the same shape as the current in the DC link, but obviously it's centered around some other value now, right? So then when now we have this new current, we get a different shape of voltage ripple. And these shapes are pretty cool looking, honestly. And they have this predicted similarly because it's basically the same method in this paper. You can see when the power factor is really bad, it does this like egg-shaped sort of thing, and when the power factor is okay, it does this like little wave shape sort of thing. Yeah, so basically recap of this video. In the previous video, we were able to determine the switching states of a 3-phase inverter based on the modulation index and the power factor. And then from that, we can determine what the current in from the DC link is instantaneously based on the switching states and having arrays for the switching state and the current in the load. And then from that, we can determine the current in from the DC bus. And then from that, we can determine the current in the capacitor. And then from the current in the capacitor, I is equal to C dV dt. We can determine what the voltage across that capacitor is, and the voltage across that capacitor is the voltage that is the ripple across the DC link. So in my third video, I think I'm going to go over this DC link capacitor with motor parameters. It's basically the same script as this, but instead of just inputting a modulation index and a power factor, you can input the characteristics of an electric machine, or specifically a synchronous machine, and it will determine what modulation index and power factor is applied to this machine, and then calculate all the same plots for you.